Welcome to Two Projects. In this video, we are going to explain the project YOLO Model Optimization for Remote Sensing Image Object Detection. Introduction. The project aims to advance object detection in remote sensing images using convolutional neural networks, that is CNNs. With applications spanning intelligent transportation, urban planning, agriculture, disaster rescue, environmental monitoring, military operations, and public security, the focus is on improving identification, localization, and tracking of objects in these intricate images. Accurate interpretation of remote sensing images is crucial for decision making in various fields. The project addresses complexities like large size, variable object sizes, and a high proportion of small objects. By leveraging CNNs, it enhances object classification and localization, providing a valuable tool for efficient planning in sectors relying on remote sensing data. Traditional methods like two-stage approaches, example RCNN, face computational speed limitations affecting real-time tasks. Single-stage methods sacrifice accuracy for speed. So the project proposes YOLO, a model optimizing object detection by combining classification and location regression in a single step. This model aims to strike a balance between accuracy and inference speed, tailored for the specific characteristics of remote sensing images. And the primary goal is to develop and implement YOLO, benefiting professionals in urban planning, disaster management, agriculture, and public sector. Improved object detection facilitates more informed decision making. Additionally, the optimized model contribute to advancements in computer vision and deep learning beyond the realm of remote sensing. Objective of the project. So, as I already mentioned, the primary objective of the project is to enhance the accuracy of object detection in complex remote sensing images by addressing challenges related to multi-scale feature learning and the trade-off between detection accuracy and model parameter complexity. And we aim to implement a lightweight coordinate attention module in the shallow layer of the YOLO model to improve detailed feature extraction and suppress redundant information interference, thereby boosting the model's ability to detect multiple objects. The goal also includes optimizing the anchor box mechanism, modifying the loss function, and incorporating a spatial pyramid pooling fast with a tandem construction module in the deeper layer to improve the model's ability to detect objects of different sizes and scales. We want to achieve these improvements while maintaining the same number of parameters and complexity as comparable models for enhanced generalization and overall efficiency. And the goal is to evaluate and compare the performance of YOLO V5 variants, that is V3 Tiny, V4, V5S, V8S, with the proposed CA YOLO model. And we want to assess multi-object detection accuracy and overall efficiency to determine the strengths and weaknesses of each algorithm variant for remote sensing applications. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of law of work. So the first step is important required packages. So the initial step involves importing essential packages such as NumPy, Pandas, Matplotlib, sklearn, TensorFlow, and Keras. These form the foundational tools for data manipulation, visualization, and machine learning, creating a robust environment for subsequent tasks. The second step is exploring the dataset. So the project involves the exploration of multiple remote sensing datasets, namely RSOD, that is Residential Scene Object Dataset, NWPU VHR10, that is Northwestern Polytechnical University Very High Resolution 10, and DOTA, that is Dataset for Object Detection in Aerial Images. So this step includes reading images from these datasets and plotting them to gain insights into the characteristics and challenges of the data. The third step is image processing. So this step involves pre-processing images, including converting them to blob objects, defining classes, declaring bounding boxes, and converting arrays to NumPy arrays. These processes prepare the images for subsequent stages in the computer vision pipeline. The next step is loading the pre-trained model. Here, the pre-trained model is loaded and its network layers are read, output layers are extracted, setting the stage for utilizing the pre-trained model for object detection tasks. The next step is image processing again. So, further image processing involves appending image annotation files, converting color spaces, creating masks, and resizing images. These steps ensure compatibility and optimization for the subsequent phases. The next step is data augmentation. In this step, data augmentation techniques such as randomizing, rotating, and transforming images are applied. These augmentations enhance the model's ability to generalize and improve its performance on diverse datasets. The next step is installing the packages required for YOLO v5 in Colab. Here, the necessary packages for implementing YOLO v5 in Google Colab are installed, ensuring a seamless integration of the YOLO model for subsequent data processing and training. The next one is processing the data based on YOLO v5 model. So, the dataset is processed in alignment with the YOLO v5 model requirements in this step. This includes organizing and formatting the data to match the model's expectations, ensuring optimal training performance. The next step is training and building the model. So, multiple YOLO v5 variants, including YOLO v3 Tiny, YOLO v4, YOLO v5s, YOLO v8s, and CA YOLO S, are trained and built on three different datasets RSOD, NWPU VHR10, and DOTA to compare the performance. This step includes configuring the model, specifying hyperparameters, and monitoring the training process. And in the next step, as an extension, exploration of additional models, that is, YOLO V5X6, is conducted, aiming to enhance the robustness and accuracy of the final predictions beyond the initial set of models. And as an extension, again, a front end interface is constructed using the Flask framework, incorporating SQLite for user sign up and sign in functionalities. So, this user friendly interface allows users to input images, triggering pre processing and detection using the trained models. So, after signing in, users input images through the front end, initiating the model detection process. So, the given inputs undergo pre processing. The pre processed images are fed to trained models, and the model infers and detects objects, applying segmentation and bounding boxes to identify and distinguish each object within the input images. And annotated images showcasing detected objects with bounding boxes are displayed through the front end interface, providing users with a visual representation of the model's predictions. Now we'll understand about the algorithms used. So the first algorithm built is YOLO v3 Tiny. So YOLO v3 Tiny is a lightweight variant of the YOLO, that is, you only look once object detection algorithm. It divides the input image into a grid and predicts bounding boxes and class probabilities directly. The tiny version sacrifices some accuracy for increased speed and reduced computational requirements. It is well suited for real time applications and scenarios where resource constraints are a consideration. The next algorithm built is YOLO v4. So, YOLO v4 is a revolution of the YOLO series, introducing improvements in terms of accuracy and efficiency. It incorporates features like CSP Darknet 53 backbone, PARNet, and SAM, that is Spatial Attention Module. YOLO v4 achieves superior object detection performance with advancements in network architecture and utilization of novel components, making it suitable for applications demanding high accuracy. The next one is YOLO v5s. So, YOLO v5s is part of the fifth iteration of the YOLO series. YOLO v5 introduces a more modular and efficient architecture, leveraging advancements in deep learning. The S in YOLO V5S denotes the model size and it is considered a small variant. It maintains a balance between accuracy and speed, making it suitable for real time applications with improved detection capabilities. The next algorithm built is YOLO V8S. So, YOLO V8, a state of the art model, excels in object detection and classification. Its anchor free approach predicts object centers directly, streamlining the process. Architectural updates such as mosaic augmentation during training enhance accuracy. YOLO V8's efficiency, developer friendly features, and continuous development make it an ideal choice for our project, ensuring precise detection in diverse remote sensing images. And the last algorithm built is CA YOLO S, or Coordinate Attention YOLO S. So CA YOLO S is a model optimized for remote sensing image object detection. It incorporates a lightweight coordinate attention module in the shallow layer to enhance detailed feature extraction and suppress redundant information. Additionally, it includes modifications to the anchor box mechanism, loss function, and employs a spatial pyramid pooling fast with a tandem construction module for improved detection across various sizes and scales. So, the goal is to strike a balance between accuracy and inference speed, addressing the specific challenges posed by remote sensing images. CA YOLO S is tailored for the project's objectives, aiming to maintain efficiency while achieving enhanced multi object detection accuracy. Now we'll see the comparison graphs. So, first we'll see the comparison graphs of the algorithms built on RSOD dataset. So this is the horizontal bar graph comparing precision scores of different algorithms. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions representing the ratio of true positives to the sum of true positives and false positives. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. Recall assesses the model's ability to capture relevant instances calculated as the ratio of true positives to true positives and false negatives. And this is MAP scores comparison graph. In this graph on x-axis I have MAP scores and on y-axis I have algorithm names. MAP, that is mean average precision, evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. These are the comparison graphs of the algorithms built on NWPU VHR10 dataset. And these are the comparison graphs of the algorithms built on DOTA dataset. So the algorithm which is best performing in all the performance metrics will be used for detections. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So these are dataset folders in which I have required images dataset on which we will train the models. This is sample folder in which I have images on which we will make the detections. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. These are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. These are Jupyter source files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password and click on login button. So it has redirected us to the object detection page. So here we can see an action link, click on it. Click on detection link. So as I mentioned earlier, we can perform the project using three different datasets: RSOD, VHR10 and DOTA. So first we'll execute the project using RSOD dataset. Click on it. So here we have to upload any remote sensing image and the application will detect the objects from the image. Click on choose file button. So from sample folder, from RSOD subfolder, I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So we can see the application has detected the objects from the image. It has drawn a bounding box around the detected objects. And we can see it has classified the objects as aircraft. And we can also see a probability score here telling us how confident the application is about the object detection and classification. Click on back. We'll try giving another image. Click on choose file button. So this time I'm selecting this image and click on open. The image is loaded. Now click on upload button. So we can see the application has detected the objects, classified them as aircraft. It has drawn the bounding boxes around them and we can also see a probability score here. Click on back, click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see the application has detected playground. It has drawn a bounding box around the detected playground. And we can also see a probability score here telling us the confidence level of the detection. So similarly, we can upload any image and can get the detections. Click on choose file button, select the image, click on open and click on upload button. So we can see the application has detected the objects. It has drawn bounding boxes around them and we can see the classification, that is oil tank, and we can also see the probability score. Click on back. Click on action link. Click on detection link. So this time we'll try using VHR10 dataset. Click on VHR10 dataset link. So we have to upload remote sensing image again. Click on choose file button. From sample folder, from VHR10 folder, I'm selecting this image and click on open. The image is loaded. Now click on upload button. So we can see the application has detected the objects. It has drawn the bounding boxes around them. We can see the classification and the probability score. Click on back. We'll try again. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see the application has detected the objects. It has drawn the bounding boxes around the objects detected. It has classified them as vehicles. And we can see the probability score telling us the confidence level of the detection and classification. Click on back. Similarly, we can execute the project using DOTA dataset also. Click on DOTA link. Click on choose file button. So from sample folder, from DOTA subfolder, I'm selecting this image and click on open. The image is loaded. Now click on upload button. We can see the application has detected small vehicles and large vehicles. It has differentiated them using different colored bounding boxes. And we can see the probability score also. Now click on back. Click on choose file button. We'll try again. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see the application has detected the harbor and the ship. It has drawn different colored bounding boxes around them. Click on back. So similarly, we can upload any remote sensing image and can get the object detections. Click on sign out. So the conclusion here is the project successfully improved object detection accuracy in complex remote sensing images by addressing challenges related to multi-scale feature learning and finding a balance between accuracy and model parameter complexity. Thorough evaluation and comparison of YOLO variants V3 Tiny, V4, V5S, V8S alongside the proposed CA YOLO provided valuable insights into their strengths and weaknesses. The analysis considered multi object detection accuracy, inference speed, and overall efficiency for informed decision making. Through an extension effort, the exploration of additional model YOLO V5X6 significantly enhances the project's predictive capabilities. This expansion ensures a more robust and accurate final prediction. And the project extended beyond model development, incorporating a user friendly front end using the Flask framework. With user authentication and seamless integration, the final outcome demonstrated real world applicability, providing a convenient interface for users to input images and visualize detection results.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.